my pleasure today to introduce our speaker, Emily Chin. Emily got her bachelor's from Tulane in 2008, and then she went on to do a PhD with C.T. Lee at Rice, where she graduated in 2013. She then went to Brown to do a postdoc with Greg Hirth and Alberto Saul. And just last August, she got a faculty position at Scripps. So she's an assistant professor at Scripps now, and has been there for a little less than a year. So today she'll talk to us from arts to continents, a deep lithospheric perspective. Welcome.
Great. Everyone can hear me okay? Thanks enough for inviting me, and had a really nice morning talking with folks here, and I'm really looking forward to the rest of the day. So, yeah, I'm going to be talking about kind of big picture view of how continental crust and lithosphere evolves from looking at the perspective from the deep lithosphere. So, and I'll explain what I mean by that in a few slides. So, as we all know, Earth is a unique planet because we have a topographic dichotomy that's manifested by the presence of two different types of crust. So we have continental crust, which is buoyant, high elevation, and granitic in composition, or andesitic. And then we have oceanic crust, which is low elevation, basaltic, and dense. And this map here shows the age distribution of continental crust, and we can see that the continental crust tends to be very old, especially the cores of the continents are billions of years old, whereas we know that the oldest oceanic crust is at most a couple 100 million years old. So why is this dichotomy present on Earth is one of the big questions in geological and planetary sciences. So how do we generate Earth's crust? We know that at spreading mid-ocean ridges, the plates spread apart, the mantle upwells, and we melt the mantle because of the decompression of pressure, and we form mid-ocean ridge basalts, which go on to form the oceanic crust. Eventually, that crust subducts because it gets cold and dense with age. When it subducts, the water and volatiles that it held because it was under the ocean for so long get released, dehydrate. That lowers the temperature of the mantle wedge, and we get melting. These melts rise up, and eventually they form the continental crust, or what we think the continental crust should look like. There's another type of magmatism on Earth that forms crust. These are hotspots, which are not related to plate tectonics, and these are associated with mantle plume upwellings that their origin is much deeper. So I'm interested in looking at the generation of crust from a deep perspective. And what I mean by that is, we sample the surface, we can go to volcanoes and sample the lavas, we can go to the granitic batholiths and sample plutons, we can drill into the oceanic crust and sample morb. But what happens deeper down? So as magmas rise and differentiate, we know that crystals fractionate out of that magma and they accumulate. So these rocks are called cumulates, and I'm showing that here schematically. These cumulates are very important because they form a large reservoir of mafic and ultramafic rocks in the deep crustal lithosphere, and we don't, unfortunately, know a lot about how their evolution plays into the role of crust formation. So I'm also interested in how the lithospheric mantle evolves during crust formation. So we know that when we melt the mantle, we leave behind a depleted, we generate a basalt, and then we leave behind a depleted mantle residue, which has been depleted of things like calcium, aluminum, sodium, to form those basalts. So how does this lithospheric mantle evolve over time? And one of the long-standing observations in igneous petrology is that these two types of crust on Earth have really different affinities. So when we look at the morbs, the mid-ocean ridge basalts, this is from a recent compilation of morb averages, we can see that on a diagram of AFM, A being alkalis, F being iron, and total iron, and the M being magnesium, we can see that morbs evolve along a trend where they become iron enriched. This is called the tholeiitic trend. And in contrast, when we look at lavas that are erupting out of subduction zone volcanoes, we see that for the most part, many of those lavas follow a different trend. They become iron depleted. So the origin of the tholeiitic versus calc-alkaline trends is one of the sort of central questions of petrology, and particularly the origin of the calc-alkaline trend, because there's been two competing hypotheses for what generates these calc-alkaline continental crust-like lavas. So the first is perhaps higher water content, because we're in a subduction zone, or perhaps higher elevated oxygen fugacity can lead to the early precipitation of iron oxide minerals, and this can drive the melt to iron depletion. Or perhaps we are assimilating and remelting pre-existing crust, which is silica-rich and iron-poor. So these are two different hypotheses, and I think the community is still debating about the relative roles of each one forming these trends. So recently I've been working with some colleagues, Kei Shimizu is one of them, who's a postdoc here. We wanted to tackle this problem, but from looking at the cumulus, the deep crustal component. So we compiled from the literature cumulate compositions from all of these localities, and here I'm just color coding it by mid-ocean ridges, which are the blue triangles, and arcs, and I've divided arcs between island arcs, which are blue, and continental arcs, which are orange. So we took all of these cumulates and we wanted to see whether we could see any trends and understand the process of forming these two igneous trends. So one of the things we found was that when we binned all the data by mg number, so here I'm showing a plot of iron, total iron versus mg number, and mg number is useful because it's a way of us telling how differentiated a magma is. So the higher the mg number, the more in equilibrium it was with its mantle source, and the lower it is, the more evolved, differentiated it is. So you can imagine granites being way out here, basalts being way out there. So when we looked at all of the arc cumulates versus all the mid-ocean ridge cumulates, we found that the arc cumulates have high iron contents at high mg number. And this is clearly shown in this plot, but it's also apparent when we separate out the different types of arcs. So when we look at just continental arcs, we see that at mg numbers of 75, which is in equilibrium with the mantle peridotite, we see considerable iron enrichment in these cumulates. We also see the same feature in island arcs, and when we compare continental to island arcs, we see that continental arcs tend to be a little more iron enriched than the island arc components. So the key message here is that these primitive arc cumulates are iron rich, and why is that? So if we think about the tholeiitic versus calc-alkaline trends and what those would predict, so we know how the melt should evolve. So how should the cumulates evolve? So what we did next was Kei has done a really nice job of doing some melts modeling of how we should expect primitive cumulates to evolve from a melt that's differentiating. So we took a primitive anhydrous morb composition, we fractionated it at low pressure, and we just wanted to see what the solid instantaneous cumulates look like. So those are these dashed lines in these panels here. And we also did a case for arc magmas where we added some amount, several weight percent of water to the starting composition. So these dashed lines predict the morb cumulates should be iron depleted early on, because as we know, the morb lavas or the morbs themselves are iron enriched, so we need to form a complementary iron-rich cumulate. And then the cumulates themselves become iron enriched later. And when we plot the actual data from the literature on these models, we see nicely that the morbs do follow these cumulate trends quite nicely. And we can see in titanium versus magnesium, most morbs can be approximated as instantaneous cumulates from an isobaric fractionation. When we look at the arc case, there's a lot more scatter in the arc cumulates. These are, there's a much thicker crust we're talking about here, so we should see more complicated processes. But overall, we see general overlap with the predicted melt trends. So when we look at the median value at a high Mg number, which is these dark, large symbols here, that iron enrichment shows up really nicely. And it might not seem significant to you, but this is greater than a 30% enrichment, and that's significant. That's very significant for a major element. So this iron enrichment is a real feature. So I think looking at the cumulates has really sort of revealed to us the nature of this pholeotic versus calcalkaline trend. So one of the ways we can form these iron-enriched cumulates in arcs is by some kind of iron-rich mineral coming out early. And it's most likely that this mineral is magnetite because we see the same iron enrichment in island arcs, which are thin, which don't have a lot of garnet, because garnet would be another candidate for these iron-enriched cumulates. And the fact that we observe the iron enrichment at high Mg numbers means that we cannot have a lot of crustal assimilation going on because you don't expect a lot of crust down at the conditions where you would have a mantle-derived basalt fractionating. So the key message is that the iron enrichment of these arc cumulates appears very early, and we infer that crustal assimilation is a negligible process in generating the calc-alkaline trends. So just to summarize that here, you can imagine the island arcs, so if we just look at the island versus continental arcs, we see that there is this slightly more iron-enriched trend in the continental arcs. And that could be for a couple of reasons. The first is perhaps thicker crust could affect the amount of melting that goes on in the mantle wedge, and that could affect the melt water content, which can therefore affect the oxygen fugacity or just the general amount of water you have available to affect the melt evolution. So that's a remaining question that we're going to pursue next. Why are these continental arcs more iron enriched than island arcs? So the roles of thicker crust and perhaps melt water content are two ideas. So the next question I wanted to address is, well, there's evidence that we know, continental crust is thick. So how does it become thick, and how does it become differentiated? So I'm going to explore that question from looking at the deep lithosphere again. And we also know that continental growth, unlike morphogenesis or oceanic crust production, is episodic. So we know that the spreading of the ridges in the oceans happens continuously, and we are generating oceanic crust like a conveyor belt that gets subducted. But we don't always get subduction zone volcanoes. Throughout Earth's history, we also see that the growth of continents, which we think are linked to subduction zones, is also episodic. So here's a plot of the apparent intrusive flux versus age. Sorry, there should have been age here. But these are for two different batholiths, the Coast Ranges batholith in North America and the Sierra Nevada batholith, and then the Andes is all shown here. But you can see that the magmatism occurs in these distinct pulses, where for a short, maybe 10 million year window of time, we get a high flux of magmatism, and then it just shuts off abruptly. And we don't know why the arc magmatism is episodic. So one of the keys is that, in order to go from these sort of thin basaltic island arcs to thick felsic continental arcs, you need to somehow thicken this lithosphere. And we know that there's this genetic link between island arcs and continental crust because when we look at the trace element compositions, the continental crust average trace element composition is very similar to the average flux of primitive island arc basalts. But how do we go from these island arcs to continental crust is the question. So 3 questions I'm going to address in the remainder of the talk are, how does this arc lithospheric mantle evolve? What controls the episodic nature of arcs? And how is the arc magmatism ultimately affected? So one of the great natural laboratories for understanding arc processes is Western North America, shown here. the Western North America is home to some of the type localities for Cordilleran-style batholiths. So in red are shown all the Mesozoic age granitoid plutons associated with subduction. And Western North America is also a very nice place to study this because we have a complete history of going from a passive margin, transitioning to an active margin, and then transitioning to a full long-lived subduction zone from about 220 to 80 million years. And shown here are these pulses of granitoid magmatism. These come from zircon age dates done by Scott Patterson's group at USC, and you can see that there was these distinct periods of intense, short-lived magmatism, and why is that? So one of the ways we can explore the deep lithospheric component is to look at xenoliths. And for those who are unfamiliar with xenoliths, they're actually fragments of the deep crust and the deep lithospheric mantle that are accidentally erupted in basaltic volcanism. They also come up in other types of volcanism like kimberlites. So xenoliths are great because they provide us like a drill core of the deep lithosphere. So here I'm showing you a schematic cartoon diagram of what we think the lithosphere beneath the Sierra Nevada batholith, shown here, looks like from xenolith data. And at the surface, we have these granitic plutons grade downward into gabbros across the seismic moho, and we get into the deep lithospheric part here. So we have pyroxenites, and these pyroxenites are thought to be cumulates of the arc magmatism. And then going further down, we grade into the actual perditite mantle, going down to almost 100 kilometers or so. And these are interpreted to be residual melt residues of the melting. So I'm going to focus first on looking at the perdites because these tell us a lot about the history of melt depletion and stabilization of the lithospheric mantle. So starting shallow, and then going down with increasing depth, we grade from spinel perdites, which are these very coarse-grained, protogranular textured samples. So this is a cross-polarized thin section scan of one of these samples. The scale bar is the same in both panels. And on the right is a SCM phase map, which we actually also collected EBSD data, which I'll talk about next, where we can see very clearly the phase assemblage. So green is olivine, yellow OPX, red CPX, and purple spinel. And you can see that these spinel perdites are depleted. They're Harzbergites, dominated by olivine. Looks like melt has been extracted out of them because they don't contain a lot of pyroxene or spinel. And then when we go down with depth, we get into the garnet stability field, and these perdites are very different texturally. They have what we would call porphyroclastic textures, meaning we have fine-grained matrix with large deformed grains, porphyroclasts of orthopyroxene. So here's a nice example of the pyroxene grain that has been bent. And modally, the phase assemblage is different. So we can see there's less olivine, more CPX, and more garnet, suggesting that either less melt has been taken out of these perdites, they're more fertile, or perhaps they were melt depleted and then metasomatized a second time. One other feature that I'd like to point out is the presence of, in this phase map, so this was all done with a field emission SEM. So these bands of fine-grained pyroxenes are a key feature that I'll talk about next. And they appear to form a lineation overprinting the deformed matrix. And at first glance, this texture is suggestive of metasomatism or sort of a melt infiltration event. So these perdites appear to have some sort of metasomatic overprint. So if we now look at just the garnet perdites, because the garnet perdites have kind of the richest textural history. They have some more phases. They seem more deformed. So there's a lot of things going on here that we can kind of extract out the pressure, temperature, compositional, and time evolution. So on the left, I'm showing a plane polarized image of a thin section, so the scale bar is the same here. And on the right is a simplified sketch of what this rock is, just for those uninitiated with looking at peridotite, this is just a nice way to see some of the textures. So there's three, what I call generations of microtextures. The first one is this original fabric, this olivine OPX porphyroplast. These are those large grains that some of them are deformed. And in addition to that, those OPX and olivine grains, we have chromium-rich spinels, which are these black minerals here. And that texture is probably related to the melt depletion, the earliest event that happened in the mantle. The second texture is these bands of fine-grained pyroxenes, and as I mentioned earlier, that could be suggestive of some secondary metasemitism. And then finally, there's a third texture, which is what we interpret to be associated with cooling, and that's the presence of fine-scale garnet and amphibole exsolution lamellae in pyroxenes, which we think, because as we decrease the temperature, aluminum becomes less stable in pyroxene structure. You can also increase the pressure, and therefore you exsolve out an aluminum-rich phase from the garnet from the pyroxene. So, if we look at the earliest event, which is probably the melt depletion, we can use the chromium-bearing spinels to give us an idea of the degree of melt depletion experienced by these peridotites. And chrome number is one of the indicators we use. The chrome number is the chromium over chromium plus aluminum ratio. And it's useful because chromium is one of the slowest diffusing species in the mantle, and it's highly compatible in spinel. So when the mantle melts, chromium likes to stay behind in the spinel, and it doesn't move around very easily. So if subsequent things happen to this peridotite, the chromium could be a faithful recorder. So these are, this is a graph of chrome number in spinel versus the degree of melt depletion, and these colored symbols are experimental studies which have been done in both anhydrous and hydrous experiments, which tracked how chrome number evolves with increasing melt depletion. So as you melt more of the mantle, chrome number in spinel goes up. And we can plot our natural peridotite chrome spinels data on here. In yellow are these garnet peridotites, and the black are the shallower spinel peridotites. And then we can essentially use this empirical curve as a calibration curve to estimate the degree of melt depletion. And if we do that, we see that, interestingly, both the spinel and garnet peridotites melted roughly the same degree. And that's interesting because, as I showed in the first, one of the first slides, these garnet peridotites have a lot of extra pyroxene, and they have a much different texture and modal mineralogy, yet they still preserve a similar melt depletion history. Okay, the next, going to the next texture that we can use to get the PT info, we can use garnet orthopyroxene microtextures to get an estimate of the final pressure and temperature. And that's because the reaction of aluminum exchange between garnet and pyroxene is highly pressure sensitive, so we can exploit that as a thermal barometer. And one of the microstructures that we used was these garnet exsolution lamellae, and the relationship between that and the host orthopyroxene. So again, this was done with the field emission probe, and the reason we used these garnet lamellae is because texturally they're probably the last thing that happened to this rock, because they're preserving these gradients in aluminum concentration that were not subsequently modified by something else. So we can use this as kind of a maximum estimate of the final PT condition. So if we do that for various different garnet OPX pairs, we get final pressures between 2.5 and 3.5 GPa, so that's almost as deep as 110 kilometers, and temperatures between 750 and 800 degrees, which are quite cool. Okay, so now we have two pieces of information, observations that we can put together and reconstruct the PT path of these lithospheric periddotites. So the first piece of information is that degree of melting from the chromium spinel data. And here on this PT plot, I'm showing just the dry solidus of the mantle peridotite, and these dashed lines are different contours of melting degree. And this red band is the range of melting that we would get from the observed cone number, so 15 to 20% is that range. And then the second piece of information we have is those final pressures and temperatures, which are here. So now the question is, well, we have this large range of possible melting scenarios. Where did these periddotites melt? And we know they had to end up here at their final PT. So the easiest scenario to think of is that, let's assume the periddotites melted at their final pressure. So in that case, let's just take 3 GPa and assume that the mantle upwelled along an adiabat. Let's just assume a dry adiabat and stopped there, melted 15 to 20%, and then just cooled, forming a thermal boundary layer that became the lithospheric mantle. So if we assume that scenario, that actually results in mantle potential temperature. So the mantle potential temperature is the temperature of the mantle along an adiabat. If you were to extrapolate it all the way to the surface, that temperature is too high for what we would consider for Phanerozoic subduction zone, or even just Phanerozoic ambient mantle. So 1500 degrees would be what we would get, and it's pretty well constrained that the mantle potential temperature today, at least since 2.5 billion years ago, is probably something more like between 13 to 1450 degrees. So if we just say 13 to 1400 degrees is a reasonable arc sort of mantle temperature, that would mean our melting interval has to be constrained to shallower pressures than the final equilibration of these periddotites. So they had to upwell shallowly, become melt depleted, and then somehow these arrows are showing paths of increasing pressure or thickening and cooling to stabilize the lithosphere that we sampled through the xenoliths. So what geologic scenarios can we imagine that we can bring mantle that forms shallow and hot to conditions that are deeper and then cooler? So here are just some ideas. The first is, well, just a prograde sort of metamorphic path where you are compressing arc terrains together or underthrusting continental lithosphere, but that should result in a PT path where you tend to heat up the lithosphere as you increase the pressure. Another idea is a flat slab subduction, because now you're impinging a very cold slab on the mantle, but most of the models for this, and also observations, don't have a slab going down to 100 kilometers, which is the final pressure of some of these deepest periddotites. Another idea is underplating basalts. So depending on where you are in this lithospheric column, if you underplate basalts, if you just track a piece of the lithosphere, you might expect no change in pressure because you're just sort of growing it below you. Finally, another idea is just vertical inflation through magnetism. And this is a complicated idea, but depending on the rates of intrusion of magnetism, you could get a range of PT paths, and then it's the relationship with that in the slab potentially could lead to cooling as well, and I'll get back to that in a little bit. So because we know that these xenoliths came from an arc type environment, something that involves substantial magnetism probably played a role, and we know that this magnetism was highly episodic and put a lot of granitoid magma into the crust at short times. And if we're doing that, we know we have to grow a mafic root and ultramafic residue at the same time. So it's not too unreasonable to think magmatic inflation probably played an important role in thickening the arc lithosphere. So I'm going to take that as sort of the working hypothesis here, and assuming that magnetism is intimately linked with forming the arc lithosphere. And if that's the case, we need to address this issue of the melt infiltration. So those deep garnet periddotites that I showed you in those earlier slides had this, these bands of pyroxene overprinting their primary fabric. And that is interpreted as a melt infiltration signature. So geochemically or petrologically, is that what we see? So we can go back to our trusty chromium and spinel indicator, and now we can plot it against something that's also the same as melt depletion, but in this case, something we can measure in the rocks. And this is clinopyroxene mode. So if we start out with a sort of primitive mantle composition, and if we melt it, we would expect our chrome number to go up in spinel and our CPX to go down. And if we plot our spinel peridotite, so these are the shallow, coarse grained samples that are olivine rich, the black symbols here, if we plot those on this diagram, we see for the most part, those spinel peridotites fall pretty nicely on this melt depletion trend, and that matches well with their observed modal mineralogy. So in contrast, when we plot the garnet peridotites, these deeper samples, which have a lot of pyroxene and garnet, we see that they have too much pyroxene for their degree of melt depletion. And that suggests that they've been melt infiltrated, or what we call refertilized. They were previously a melt depleted spinel peridotite like this, but they've had a melt added back, which increased calcium, aluminum, and therefore increased the amount of CPX and garnet. So when I was at Brown, I worked with Greg Hirth, who does a lot of microstructural sort of studies on peridotites, and we wanted to kind of also look at the fabrics of these peridotites and see whether we could, tease out the compositional history and the deformational history. So what we found is when we looked at the olivine fabric, so this is again those SEM maps, so actually in each of these maps we took a very small grain spot size, and we, at 7 micron step sizes, we collected both a compositional data point and a crystallographic orientation data point. And so these maps yield a wealth of information where you get both the composition and the crystallographic orientation of each of those minerals at each step. So the olivine system, or mineralogy, you can just explain by three main axes, A, B, and C. And what is shown here are pole figures of the concentrations of those axes. So if we see a lot of, strong concentration, strong closely spaced contours, that means a lot of those, the A direction is highly concentrated. So what we found was that going from shallow spinel peridotites, the fabric changes. And I'm not going to go into all the details, but I'm happy to talk to anyone afterward who wants more information on this. But basically, what we find a very strong orthorhombic fabric. So you can see here, these maxima are very strong. But then as we go down into the more pyroxene-rich, finer grain samples, this fabric, or the concentrations of these axes become weaker. And you can see how, there's no strong maxima in this sample except for the V direction. And this is because the V direction is the glide plane. So this is a lineation here. But anyway, the main point is that with increasing depth and increasing degree of fertility, the olivine fabric changes from a strong fabric to a weaker fabric. And these sort of weak axial type LPOs, lattice preferred orientations, have been both experimentally and shown in nature to correspond with a grain size sensitive creep mechanism, which could be related to melt infiltration. So as you infiltrate melt into a peridotite, that melt crystallizes new minerals, fine grains of those new minerals, and the deformation can be concentrated in these fine grained regions. So this is good evidence that we also have melt infiltration that affected this lithospheric column. So as I mentioned here, one of the sort of ambiguities in looking at xenolith work is we don't always get a good idea of the sort of structural context, right? Because these are just fragments of mantle, and we just look for sort of strain indicators within the samples themselves, but that's not always the best way. So one thing we can do is we can actually look at individual grains of minerals and look at the deformation structures, microstructures inside them. So one example is looking at the orientations of low-angle subgrain boundaries in olivine. And olivine is nice because the symmetry is pretty simple, and we know the dominant slip systems pretty well and how they behave with pressure, temperature, and water content. So just briefly, what we can do is we can map each of the grains. So again, this is the same map that I showed earlier, but we now process the data a little differently to just look at individual grains. And we see within some of these grains, so this is one grain here, this has a subgrain boundary, so an area of different orientation, not big enough, not greater than 10 degrees, so it's not a new grain boundary. And we can look at the orientation of that subgrain boundary. And that subgrain boundary orientation tells us something about the dominant slip system that was active to form it. So in this example, the subgrain boundary is perpendicular to the A direction and appears to have a rotation axis around the B axis. So we can go to our table here, and you can derive this table yourself from just the olivine symmetry, and for both tilt or twist boundaries. And you can say, all right, what subgrain would form perpendicular to A or parallel to the A plane? So that could either be this one, an E-type boundary, or it could be a C-type boundary. And which one would have a rotation axis around B? And the only one that matches those two criteria is an E-type subgrain boundary. And we did this analysis for many, many subgrains. So you can see, like, taking this whole map and just finding all of the olivine grains that had these low-angle misorientations. And we found that E-type subgrain boundaries, like the one I just showed you previously, were quite dominant. And the E-type fabric, or that LPO, has been shown to be one of these hydrous, these slip systems that are activated when you have elevated water content in the olivine. So unlike what we could just tell from the bulk LPO, those pole figures I showed you, this sort of analysis can really reveal a lot more information, particularly in xenoliths, which are challenging to do EBSD on. So the next thing we wanted to test was, well, if we have evidence from the microstructures of high water content, do we observe high water content in the non-monohydrous minerals? And what we found, at first I was very disappointed when I saw this. So we did water measurements using SIMS on pyroxenes and olivines and garnet, and the olivine water content was too low to account for this E-type fabric. So this is a plot from Phil Skemmer et al., where they look at natural prototypes, but also these are experiments, and the sort of critical water content for transitioning from your normal dry A-type fabric, which most of the mantle appears to be, to a more hydrated fabric, like one of these E or C-type ones, is about 40 ppm. So the maximum water we got was like 10 ppm. And even if you kind of correct back this olivine water, because often we're concerned that a lot of the water gets lost through eruption, even if you correct it back to be in equilibrium with, say, pyroxene, which we somehow believe holds on to its water better, we still don't reach a 40 ppm water in the olivine. So the only sort of explanation for this that made sense was that, well, perhaps these subgrain boundaries are actually like a ghost signature for hydrous melt infiltration. So the water, as we know, diffuses really quickly, but it could take, because the way dislocations move, they're coupled with a lot of other cations, and perhaps there's a decoupling between just the water and what the subgrain boundaries, that the sort of final equilibration of those. So when we put this all back together with that PT path, which we showed earlier, how does this sort of deformation and water content data play into it? So we know we had melt depletion, shallow. We know we had some melt infiltration event. And we can now better constrain where that happened. So we know that it was most prominent in the deeper garnet-bearing ferritites, so the ones that had garnet. So we know it had to happen in the garnet stability field, or else, why do we have all this extra garnet? And we can actually do better, and we can reconstruct the last solidus at which those melt-infiltrated peridotite were in equilibrium with the hydrous melt. And so we can take the water contents of all the minerals that we measure, we can recalculate the olivine water back to equilibrium with pyroxene, and doing that calculation would put us at a solidus here with about 0.01% gold water content. So after this melt deformation event, melt infiltration event, which we also probably associate with deformation because we preserve those subgrain boundaries, and we preserve a weak overall olivine fabric, which supports melt infiltration. We cooled the lithosphere and ended up here, right, at around 3 GPa, 750 degrees. And if we think about the sort of viscosities of the lithospheric mantle at these different conditions along the PT path, we can see that at conditions here, where the melt depletion and then the subsequent kind of melt infiltration happened, we have the capability of holding a lot of water. So this is a theoretical solubility limit. Obviously, these peridotites are undersaturated, but this is just a maximum bound that we can think of as just as a thought exercise. And we have low viscosities, which are comparable to what we would think for the mantle wedge. But then somehow, this condition needs to transition here, and I think the key is that we're thickening it and cooling it, and the cooling has to happen on a time scale where we don't advect away this sort of low viscosity mantle. So we'll explore the cooling rate next. But the key is that at this condition, the effective viscosities of the mantle are so high that you can't deform it anymore, and you're stabilizing a thick, cold mantle. And the water content, the theoretical water content solubility in olivine is also much lower. So it's dry. And that's one of the keys for how we can stabilize these arc lithospheric mantles, and an analog for that is perhaps the Archean lithospheric mantle, which is also thick, cold, and dry. Okay, so the last part I want to address is the cooling rate, and this will get back to the episodic nature of magnetism. So we go back to this great texture again, which is this garnet exsolution lamellae, which has yielded so much information. And we can use it as a geospeedometer in this case. So previously we used it as a geobarometer, a geothermal barometer. But we can actually use the kind of the aluminum depletion in the orthopyroxene and the formation of garnet as a cooling time scale. And here we're just assuming that this happened at a constant pressure, at the final pressure, because this could also be due to changing pressure. And not to go into all the details, basically we explored a different parameter space of diffusivities and parameters for doing this modeling. This is just a simple 1D diffusion model. And I'm showing in these two panels just two different cooling timescales. So the E-fold cooling timescale. The first one on the left is very fast, 3 million years, and then this one is slower at 15 million years. And these different colored curves are elapsed times in the diffusion model, and the circles are the actual data for a transect from far away from a garnet to close to the garnet. So you can see far from the garnet you have high aluminum, and then as you get closer to the contact, the aluminum in the post-pyroxene becomes lower. So we see that the best model fits are those profiles that occurred in fairly short timescales, between 5 to 10 million years, and at fast cooling rates. So we need a scenario geologically that explains this rapid cooling, and it has to occur deep and at cold temperatures. But we also don't know whether this cooling was coeval with demagnetism. And we don't have any age constraints because it could have happened during the eruption, which was far after the subduction happened. So in order to address that, we did some geochronology on pyroxenites. These are cumulate xenoliths, so the second type of xenolith. And the reason we did that was because there's just a lot more garnet in these samples, so we have enough material to date. But we also looked carefully at the sort of pyroxene systematics, and we saw that there's similar zonation in aluminum in the orthoperic. So we go from high aluminum core to low aluminum rims, which suggests some kind of similar cooling history as those peridotite. And we also know from thermal barometry, because some of these have both garnet and orthopyroxene, that many of these high magnesium pyroxenites formed in the lithospheric mantle at the same pressures and temperatures as the peridotite. So we can confidently say that they were probably happening at the same time. So we dated two pyroxenites. The first one is a shallower one in the crust, about here, 20 kilometers or so. And then the second one is a much deeper one, coeval with the peridotites. And first thing we found, which was reassuring, was that we did not get an age of the young eruption, but we got an age coeval with the Sierra Nevada batholith, which suggests that these cumulus formed as a complement to the granitoid magmatism. The interesting thing, though, was that the age systematics, so we did a simultaneous spike to get both the lutetium, hafnium, and a samarium neodymium age at the same time on the same sample. And what we found was that the shallow sample, this one in the lower crust, had a large difference in the ages, so 24 million years, which is far higher than the analytical uncertainty. But the deeper sample basically had the same age between lutetium, hafnium, and samarium neodymium. And it's been known in metamorphic rocks that lutetium, hafnium quite possibly has a higher closure temperature compared to samarium neodymium. So this would make sense here, where we get an older age for the lutetium, hafnium age, and then perhaps as the rock cooled, it had to have a cooling history that we could have enough time to differentiate those ages, and that locked in the samarium neodymium age later. Okay, so the diffusion modeling tells us that we had to cool our lithospheric mantle very quickly, and it had to happen deep. So, and it had to happen during subduction, because we know that from the age constraints. So how do we do that? So one way is perhaps to involve the slab. So if you start out with a lithosphere, arc lithosphere here in the early stages of subduction, it's not as thick. You can see that there's a large window for melt generation. So this is when you're building up all that granitoid batholith, and you're subsequently building up a mafic root beneath it. As subduction continues, this magmatic inflation grows this root, and if we don't change the dip of the slab, we're just now changing the upper plate, overriding plate, well, this lithospheric mantle beneath the arc can get thick enough that it reaches about 110 kilometers, which is the average depth of the slab. And once it does that, it's going to shut off the magmatism, because now you don't have any mantle wedge convecting, you don't have any way to get melt out. And this condition right here is probably represented by these deepest garnet peridotites, which preserve this fast cooling from the aluminum depletion halos that we modeled, and also from the age systematics, because if we think about it, we needed to cool rapidly enough to get the same age in both chronometers. So finally, one way to further test this was to just do a simple thermal model of the lithosphere. So we assumed a 100-kilometer thick lithosphere, and at 100 kilometers we juxtapose it to a slab, and that slab is really cold, like 600 degrees Celsius. And this temperature versus depth plot are just different time slices through this model. So this is just a 1D conductive cooling model, and you can see that we have this abrupt cooling, and then it slowly, after 70 million years or so, re-equilibrates to a new ambient geotherm. So if we take this same model and just plot it through temperature time for different depth slices now in the lithosphere, and we compare that to the samples we have, we can infer the following. So these different temperature depth time slices, so this would be for a shallow slice at about 40 kilometers or so, and then these blue ones would be for one very close to the slab at 90 or 100 kilometers. And this, I highlighted this red one here because that could be what this lower crustal, shallower pyroxenite, that could be the cooling history of this, because we need to have enough time to pass between the lutetium, hafnium, and samarium neodymium ages for us to record that large difference in age. So we think that the shallower lithosphere in the lower crust had to cool slower, and then the deeper parts were affected by this rapid impingement on the slab, and that overlaps with our interpretation for this same ages that we get for the deep sample. And finally, on top of this, these black lines are the cooling rates for that diffusion model for the aluminum depletion. So you can see here a very fast cooling rate matches pretty well these deepest samples that have the no difference in ages. Okay, so in the last few minutes, just wanted to wrap it up in terms of what the big picture is for this Arctic lithosphere beneath the western U.S. So the root beneath the Sierras, it formed quickly, and that makes sense with these rapid pulses of magnetism. You need to form a root just as quickly. But somehow it remained intact for a long time. In this case, almost 100 million years went by from the time when we had this active arc magnetism all the way to when that arc delaminated. And we have seismic geophysical evidence today that there is no thick lithosphere beneath the Sierra Nevada batholith, and one idea is that it was delaminated. So we had this active arc. During that time, we built up granitoid batholiths. We also built up the thick root, and this is where we record the melt depletion, melt infiltration histories, and all of those deformation structures. Around 90 to 80 million years, the arc began to terminate, and it happened quickly. And if you look at the record of granitoid magnetism in the area, there's an abrupt termination at ages, after 75 million years, there's nothing. It just ends very quickly. So one idea which challenges the commonly held one of this shallowing laramide slab is that the upper lithosphere grew very quickly, impinged on the slab, and then that was actually what choked off the arc and ended it. So now, going into the Cenozoic times, the slab systematics changed, were complicated. There was rollback, then we subducted the trench, and now we have the transform margin. So during that time, probably during that opening of the slabless window, this is when this thick root started to become unstable. And the eruption of those xenoliths that I've been talking about this whole talk happened at 9 million years ago, far after subduction ended. And then it sampled, this thick root, but then at 3 million years between this time and this time, there's evidence that we didn't have any more garnet-bearing xenoliths, because the xenoliths that erupted here are really shallow. So that's taken as evidence that the root foundering happened very recently. Okay, so let's just revisit those questions I posed in the beginning about the PTT evolution of this arc lithosphere. So how does the lithosphere grow? Well, the prototype data show that we have to have this shallow, moderate to high degree melt depletion, and then a subsequent thickening and cooling of the lithospheric mantle. And this has to happen within a reasonable time frame that we don't have advection that carries away that lithospheric mantle. So if you think about island arcs, they stay thin because they're extensional, right? So there's a back arc basin that continually advects away the lithosphere you're forming, whereas in continental margins somehow, and mature island arcs, so ones that thicken enough that they have the internal compression, it transitions to this thickening regime. Okay, and then why is the magnetism episodic? So I think it's all in the upper plate. You can modulate the tempo of magnetism just by magnetism itself, basically thickening it and then not having to do anything with the slab dynamics. So many of the current views on episodic magnetism invoke a changing dip of the slab, but this seems quite arbitrary, or subducting a oceanic plateau whenever you need to shut off the magnetism. But I think this is a much more internally consistent idea of how you can have this episodic pulses of magnetism. And then you had the rapid cooling, and that stabilized the lithospheric mantle for a long time. And as we know, in the western U.S., we had the presence of a slab for a long time until the Cenozoic times. And then finally, how is the magnetism affected? And this is sort of future work. So our idea of a primary arc magma is definitely going to be affected by all of these deep lithospheric processes, because now you're forcing your primary arc magmas to go through metasomatized lithospheric mantle. So not metasomatized mantle wedge, this is lithospheric mantle. And the thicker crust in lithosphere is only going to promote that. So we have to think about how the fractionation of a lot of CPX and garnet, which is going to deplete calcium and aluminum, is going to affect the primary arc magmas coming out. So this is potentially a realm for experimentalists to explore, or getting more samples from the field and doing these sort of merged studies. So I think that's all I had for now, and I'll take any questions that you have. Thanks a lot.
So, this sounds pretty complicated story. The one thing that I got is you need a lot of material to thickening, right? And this is pretty substantial, but I assume it's also associated with the subduction.
Yeah.
So can you estimate the rate of subduction and plate motions at that time? Is it consistent?
This is a great question. So, a sort of lower bound for like the mafic, like Pelzic ratio, so the amount of this deep lithospheric component to the shallow stuff is, a minimum is like 2 to 1. It could be as high as 10 to 1. And then the subduction parameters for this time, it's known, but I think there's a lot of uncertainty because it's hard to go back this far and kind of, we have a much better idea of the present day plate motions. But there has been evidence that you had a period of higher convergence, and that could have actually promoted more corner flow because you have a lag of the magmatism. So you have this high convergence, and then after that, it seems to be that you had this flux of magmatism. But I think that's still something we don't know very well. But we do know pretty well the ratio of what, and I've actually did a really back in the envelope calculation. So I wanted to know, well, how much of this sort of mafic arc stuff has formed since like 2.5 billion years? And if we just assume these lower 2 to 1 estimates for the production, it's not a small number. It's almost the same as the amount of oceanic crust subducted. So this can be a very good way of recycling crust back into the deep mantle when you form it and it gets thick enough and dense enough to go back. And it's been happening at least for the whole Phanerozoic, as I'm saying.
It's a really nice study, a lot of different angles approaching this problem. Now, do I understand right that you want your xenoliths to have melted to a high degree and stop melting at a shallow depth?
Right.
But then you need to move them to greater depth.
Right.
You need to basically move them to 60 kilometers.
Yeah, something like that.
Right. And so you propose to do this by magnetic underplating between the base of the crust and these garnet pyrrhotite xenoliths.
So it's probably not just purely magnetic, because we know, at least, I didn't mention this, but I should have, that, the plate motions for this time have the North American continent overriding the trench. So you had and you have evidence from, I wrote a paper on metasediments in the lower crust that showed you had underthrusting of continental material. So you had thickening from tectonic processes that was superimposed on this high flux magnetism. So I think in real life it's a combination of both magmatic and tectonic. You can't just do it purely magnetically.
But it seems to me that the reason that you need these xenoliths to initially form shallow is because you're assuming dry melting.
Yeah, so that's a great question. So we did think about hydrous melting, and it still has to be shallow. It still has to be shallower than the 3 GPa. And the other thing is we should expect some hydrous phases present in the residue perhaps, because like we looked at the amphibole stability, and there should be some left in the residue. But the other thing, the biggest issue with that is the temperature. So Cynthia and I had a paper in 2015 where we used the magnesium and iron bulk composition of the pyrrhotites to estimate the melting temperature, because we know the melt and magnesium are very strongly correlated. And the melting temperatures for these are 1300. And it's really hard to imagine hydrous melting, happening at such a high temperature. We probably expected 1,000 or lower. So just from the magnesium iron systematics, it's more consistent with the sort of decompression of the sort of dry decompression melting, which we have a strong component of in the mantle wedge, right? It's just, I'm not arguing that we don't have any hydrous melting. It's just that for some reason these guys are just recording that sort of hotter nose of the wedge melting, or core of the wedge. But yeah, thanks for bringing that up.
Laura.
Yep.
So it's funny, if I hadn't heard your conclusion, I would have said this was a beautiful study proving flat slab subduction and happening under the western US, right? So you're arguing that the rapid cooling that you're seeing is evidence of no flat slab subduction.
At least not in the central part. So perhaps in the southern, so like Jason Slaby has a model where the southern Sierra appears to have its mantle sheared off, and you could have.
Well, but flat slabs are typically at 100 kilometers depth. It's a perfect depth for this story. So the flat slabs that we have today. So I mean, you say that flat slabs are arbitrary, that you just have them show up. We have 3 right now in South America alone. They do come.
So is that still a flat slab with an active mantle wedge?
So
above it?
but if you have, I mean, so your classic flat slab story would be that you have typical arc processes going on, including the types of depletion that you're talking about. And then as you impinge, as you flatten that slab, which usually happens by this overriding plate motion that you described, right? So it's not the plate coming up; it's the plate failing to sink,
Right.
the continent moving over it. When you have that, you suddenly shear off access to the semispheric corner flow very abruptly.
Right.
with a flat
So
slab.
that's exactly kind of this scenario.
Exactly,
Yeah.
but that's my point, which is it seems to me that to grow a mantle lithosphere that's not moving in the presence of active corner flow is a process that can't just happen that fast. Whereas a flat slab is a process that will happen, at least relatively speaking, as soon as you cut off that corner flow because of the retreating plate,
Right.
you cut off access to that heat source. So if you want something to stay at the same pressure and drop in temperature precipitously, the easiest way to do that is to move that lithosphere over a plate that is no longer sinking.
Sure, but it did still have to increase its pressure, right?
Well, but that happened before, right? You have your melting, and then you had it still hot and dropping to depth,
Sure.
and then you have it moving.
Okay,
back.
yeah, so it's like this sort of quick decompression and then just cooling, which is kind of what this
the cooling,
this PT path
the
had.
cooling part, to me, you don't get a rapid cooling at a
Kind of like
pressure.
you're
Right,
forming
so
it,
basically you're
and then you're bringing it very deep, and then you just cool it. That's
Right.
kind of what we concluded here, because we had to have this component of deeper melt infiltration that formed the garnet-rich areas.
Right,
So
and
yeah, I
how
think
is that not like the impingement of a flat slab right there? Like, I'm confused. I think it's a really interesting study. It's just coming up with a completely different conclusion from what you're coming up to.
yeah. Well, then how do you?
How are you forming a mantle lithosphere that is?
Well, let me ask you this: how do you cool it so quickly that you have the preservation of these aluminum zonation histories in the minerals that only happened within 5 million years?
Cold plate underneath it and removing.
But that cold plate has to be the slab.
Yes, exactly.
Sure. So I think we're on the same page here. It's
It's
just
the slab, but why wouldn't?
so I think we can
But what I'm
agree
saying
that
is that's much easier to do.
right. I think we can agree that it's the upper plate that's playing the key role. That you need to thicken that, and that affects the sort of slab
Right, but
mantle
my
wedge
point is,
dynamics.
you don't thicken something overnight, right? You're not going to create 60 kilometers of lithosphere root in a million years.
Right. I don't think it could, I mean, probably not a million years, but it's probably coeval with those episodic windows. So, like, those last about 10, 15 million years of high flux flare-up events where you're forming most of these granitoid
But you're
rocks.
arguing for cooling over the course of 3 million years.
Right, but that's the final cooling. So you could be forming this root for like, 10 million years, and then as soon as you get close to this cold isotherm where the slab surface is, then you're cooling very quickly. But the actual formation, so there's a difference here. I'm just getting the cooling rate, right? Not the thickening rate. That I don't think we know very well. But we know it probably has to coincide with those 10, 15 million year windows of flare-up magnetism, because you have to form this mafic stuff when you form all these granitoids. Where is that going to go?
Well, why isn't this lithosphere getting carried off by sea surface?
Because you also have the overriding North American craton, right? That's forming this overall compressional regime. So I guess what's happening like the Central Andes, where you have the overriding Brazilian, because you have this really thick crust, and you probably have thicker lithosphere there also.
No, actually, it's gone.
Okay. Well, this episodic thing could have formed.
The lithosphere is carried off by subduction everywhere we look. We don't see rigid mantle lithosphere under arcs anywhere.
Yeah, we have xenoliths, so.
But we don't see it seismically.
Yeah, but I think from the xenolith record, it exists, so we perhaps.
Well, you see
Like-
depleted material, but you don't see. You're not seeing something that's reflecting this lithosphere from itself.
Let's continue the rest of that conversation. Anybody else with any?
I was going to ask about the lutetium SMNDAs. Are those on whole rocks or mineral separates?
In the show I should have. There are 3-point isochrons. We did garnet, pyroxene, and whole rock.
So how do we know those aren't so solid as re-equilibration between those pairs? Because you see that a lot in the lithosphere. You only really trap the old ages when you have whole rocks where the diffusion, your mineral diffusion distance is large enough to prevent re-equilibration. Most xenoliths from the compound, for example, SMD isochrons will come up with the eruption age.
Right. Well, I think if it is subsolidus re-equilibration, that's still consistent with this being that equilibration happened at the time of the arc being active.
I mean, could the xenoliths be 200 million years old? Could they be older than the
Oh, I see. And then they just re-equilibrated
yeah,
at 90 million years.
It went down to blocking temperature.
Yeah, probably not, because Cinti did a really nice rhenium-osmium study on these that showed Mesozoic rhenium depletion ages. So they're probably related to the Mesozoic subduction. And we had subduction for most of the Mesozoic, so most of those rhenium data support not Precambrian ages.
I just have a quick question. So I did notice some of the data scattering, and you kind of didn't really explain. And
Sure,
you had a
which-
couple of the chromium low concentration, which indicates so
The
why
chromium data?
Yeah, why the melt infractionations you
Oh, like the-
came to- yeah. So what's those?
So I guess the main point is these sort of 5 or so points that. So first of all, there's only about 25 samples total, and the ones that are freshest, we can do this kind of analysis. A lot of the chromium breaks down during late stage
Yeah, I
processes.
understand that. So do you have explanation for the low concentration? So and
Like these?
Yeah. So those are kind of.
Yeah, so those could just be like maybe they just look like fertile mantle that perhaps didn't melt as much. And yeah, there's those 2 samples that seem to have lower chromium. But I think for the most part, you can agree most of the samples plot in this higher chrome number range where they appear to have these higher melt depletions.
If anybody wants to meet with Emily later, let me know. Her schedule's full, but if you want to have a conversation. And feel free to join us for lunch, so let's thank her again.
Good, pretty comprehensive study. It's always unique. It's always more complicated.
Yeah, I know. I know, it's like, oh, you guys are thinking like samplers are junky. Yeah, they're really nice.
Okay, I'll join you guys a lot.
Okay, thanks, Mike.
This thing was like working on it tonight.